Okay, so we've got a couple questions to address here in office hours right now. I'm going to read through them, so if you just came in the room, feel free to add your question to the chat. This is what I've got for our list. Emissions Prep Activity 2, questions 1, 3, and 5. And then Mastery Questions Set 3, Question 2, and Question 5, particularly 5B. So we can take a look at all of those. Let me go ahead and take a look. We'll start with the prep activity. Oh, and we might do this on Excel. But let's start with conceptual. Before we jump into Excel, let's just start with our conceptual understanding of what these questions are trying to get us to do. So all three of these parts are trying to get us to think about how line fits work. What's the point of them? Why are we making you use Excel? Is it because we're just mean? No, it's actually because Excel has some really nice functionality. The first question has us do a plot of Planck's equation, energy of the photon equals Planck's constant times, that is the Greek letter nu. Sometimes I refer to it as swoopy V. But the Greek letter nu, that stands for frequency. We're given a set, so this is for prep 2, problem 1. We're given a set of data that is, oh wait, no, I'm looking at the wrong thing, aren't I? We're given prep 2, problem 1, we've got this equation for the Planck's equation, which we can also use the information about light to turn into hc over lambda, which I will write suggestively as hc times 1 over lambda. Now I'm doing that particular thing, and this is going to be what we're doing in part 2 and in part 1. I'm doing this particular thing because it's going to make it so we can see the mathematical relationship here. Y equals mx. Right, skipping this other part. Or we can have y equals mx. So for part 2, we're going to use the h nu thing, where our slope is going to be Planck's constant if we have frequency on the x-axis. For part 1, Planck's constant times the speed of light will be our slope if we have 1 over lambda on the x-axis. And to hit this point home, what part 1 has us do is it has us make 2 different plots. It has us make a plot that's energy of the photon versus wavelength. And if you do this plot, you get some sort of curvy line. You don't get a straight line. And then it has us do an energy of photon versus 1 over wavelength. And you should get a straight line. And the whole point here is if you try to fit this, and we can still force a linear fit to both of these plots. And if you fit a linear fit to this one, you get this really bad curve. We were actually just looking at this in a different problem, this exact idea. You get this bad kind of fit. And you can look at this and say, no, that's not linear, right? That's not actually, the data is an inverse function. It's not linear. Whereas in this case, we're going to get a nice linear fit to the data. So what part 1 is asking us to do is plot the data, figure out what the slope is for this thing, which should be terrible for our data, and then figure out what the slope is for this one, which should be fantastic for our data. So this gives us a way to kind of model whether we've got a direct dependence or an inverse dependence. This is going to be a really important concept. Go ahead, do me a favor, use the participants, click on participants. This is a yes/no question. You are going to take another quarter of chemistry. That is to say, you're going to take 125 or 128. Okay, pretty much all of you, one person out of here, almost everybody is going to be taking the next quarter of chemistry. This idea of, is your data linear is your data directly dependent on something or inversely dependent on something? That's going to be really important when we start looking at kinetics of reactions. How fast do reactions happen? Next quarter, but this lays the groundwork for that idea. It also shows us how if we didn't know the mathematical function we were trying to represent, we could actually plot the data a bunch of different ways and figure out which one fit best. And that can give us some information about the physical world, actually. So that's trying to show the power there. One thing that's kind of funny is for the last two boxes on this question, you only want to put the word linear or the word non. You put linear if it's a linear plot, and you put non if it's a non-linear plot. For these short word answers in LabPal, it has to be a direct string comparison, which means it has to be the exact same letters it's looking for. It's going to count it wrong. So make sure you're putting in the right things there. That's prep 1, is looking at the difference between these two plots. And any questions on that before we go on to prep 2 part 2? Okay. So in prep 2 part 2, it's trying to represent another. We're really selling the statistical analysis and the use of LabPal here. So in this part, it's trying to say, well, why do we make you do a linear regression line? So it gives you a set of data, and it gives you energy of photon and frequency. And you've got a bunch of different data points here. I think it gives you something like 12 different data points. It's a whole bunch. And from each of these, from each one, you can calculate Planck's constant. You can do energy of the photon divided by frequency. And theoretically, every one of those calculations, Planck's constant is supposed to be constant. So it should be the same for all 12 of those calculations. However, we're going to have some variation in terms of our measurements because we don't measure perfectly, right? This is trying to represent real data. So when we look at this, we'll notice that we get a variety of values. None of them are perfectly Planck's constant. So when we look at that, we say, okay, we all agree doing one data point is not going to give us the best value. What should we do? If we can calculate it 12 times, what would be the next best thing rather than using individual values? You don't have to answer now. You should all be answering. I know you're all muted, but you can like yell it in the room where you are. If you're watching this later, yell it where you are. You got 12 data points. How are you going to get a good value for H? That's right, average. You could take the average of all of those values, and you're still going to get something that's not that good. Well, maybe it's better, but it's still not necessarily that great. And so we say, okay, well, what's the next level of statistical analysis we could do? And that's where you say, okay, well, I'm gonna take a plot that's got all these data points, and if we have real data, it's got this kind of like clustered effect, right? And I want to make a line that's going to try to be as close to all of the points as possible. I'm not going to be able, like the made-up data we use, it's really easy to get something that's like perfectly along everything. But with this, I'm going to have to kind of like estimate and be like there looks pretty good. It's it's next to most of it. It's off from a couple of them. And this is what the computer does. Except for when you do that linear fit in Excel, I know it just pops in a second, but it's actually making this line essentially 10 million times, tries a bunch of different spots, and finds the line that has all of the data points have the smallest distance from the line. So it's minimizing all of that red to make it, and it does it in terms of the squared. So that's your r squared term, right? So the r squared is how well does your line fit to the data. It's another level of statistical analysis, and it essentially is doing a bunch of calculations we don't want to do by hand. So when you've got a bunch of data points, if you can make a linear plot, you're going to find that you can do better statistics than just taking the average. So you're going to get better fits. You're going to get things that match more closely with your data. And that's really what part 2, the data analysis of Planck's constant, is trying to do. So we're looking at emissions 2. Right, 1, 2. Okay, someone asked for emissions 2, question 5.
I was actually going over like emissions, the emission questions graded, not the prep. Like
the emissions questions, number 5. Okay.
I could read it if you want.
No, I've got it right here. I just wanted to make sure I wasn't forgetting anyone's questions. Did that. So, Catherine, did that make sense? Did that cover your question for question? I guess question 3. We didn't do question 3 yet. So question 3 is an application of these 2 ideas. We've got to take the data. We've got to figure out how we're going to represent the data. And I just remembered this. Oh, this one has a funny thing in it. Let me share my screen with you real quick, and I'll show you the kind of some of the funny things, and we'll look at this problem. But again, it's going to be the same type of idea where we want to try and fit the data to a mathematical equation. So let's go ahead and take a look at this in Excel together. What I've got here is I've got some of my data copied over. Let me copy that other data. So that's the kinetic energy data. This is the speed data. We've got to insert, so this is kinetic energy. This is velocity, and the equation we're trying to represent here is kinetic energy equals 1/2 mv squared. So when I make my plot, I'm going to again want to think about what I'm trying to represent, and I'm going to want to make a column that's v squared, which is going to be equal to that thing squared. And again, by double-clicking there, it's going to copy my equation down, and Excel is smart enough that it knows I want to square the next thing down. We then make a plot that's going to be, let's see, I have to think about the equation. I didn't write down the equation before I switched to Excel. So we're going to want y equals mx plus b, and we're going to want that to be related to the kinetic energy equals 1/2 mv squared. So I'm going to want velocity squared on my x-axis and kinetic energy on my y-axis. I'll do the lazy way of doing that, where I just bring my kinetic energy over, highlight that, hit insert, xy scatter, ta-da! I'll double check. I've got values between 11 and just over 100 on my y-axis. That's my kinetic energy. And I've got values between 400 and 4,000 on my x-axis. That's the velocity squared. I'm going to go ahead and put in a linear fit with an equation and an r squared. And I'm going to make that equation real easy to see. Great. But what does it mean? So, we can run through these kind of Excel activities all day long and kind of do linear fits. The part that's interesting is what information about the physical system can we get out of it? Let's go. So back on the board, we can start to kind of think, was my Excel sheet not being shared with you? I might have messed that up. So if we look at this, we've got our equation for a line, y equals mx plus b, and we've got our equation from Excel. The equation I got was y equals 0.0289x plus 0.345. Really 346, but 345-ish. Right, so theoretically, looking at this equation for kinetic energy, y-axis is kinetic energy, x-axis is v squared. This plus 0.345 represents some variation, some error, something in the measurements that are kind of throwing off the ideal. Because ideally, zero kinetic energy would be zero velocity. Here we've got some error. The thing that throws a lot of people off is we have to realize that this slope is 1/2 the mass. So a lot of people just take the slope and think that's the answer. We have to always think, what's the actual physical thing that I'm trying to represent? And here we get slope is equal to 1/2 mass. So in order to get mass, we have to double the slope. Other thing to think about, always check your units. This question is asking us for the units in grams. Is our slope in terms of grams? And the answer is actually no. When we look at the kinetic energy, the units for kinetic energy is given to us in joules. And a joule is a kilogram meters squared per second squared. So when we get our mass, it's actually going to be in kilograms. So you have to take your slope, multiply by 2, and then divide and multiply by 1,000 in order to get it into the correct units. Okay, question number.
Could you show us how you did that on your Excel again real quick? Like how you put the numbers in and what equation you use?
Yeah. So can you see, let's see if I can make sure I share my Excel. Can you see my Excel all right? Hopefully you can all see my Excel right now. So this was the kinetic energy values. This was the velocity values. Your values are probably different than mine. Because we know that the physical equation we're trying to represent is velocity squared, I created a little equation here that just took the velocity and squared it. And then because I'm a little bit lazy, I just made a second column of kinetic energy so I could just highlight these two and make a plot. If you're using a Windows system, the first column will be your X values and the second column will be your Y values. On Mac systems, it doesn't behave the same way, so you got to watch out for that. But then I just made that plot. I got this equation, and we go from there.
Thank you.
You bet. So, weird. I'll be curious to see how the video recording did that, because I switched. Turns out I can immediately switch between things that I'm recording by clicking little icons. I haven't done that before. Hopefully that's not ruining the recording. Make sure I'm back on the right screen. Okay, so that was emission 1 and 3. So emissions questions number 5 was figured out. We can go over that one still if other people are interested. But that brings us to mastery questions set 3. We've got mastery questions set 3, problems 2 and problems 5B. Let me find those real quick. So 2, I'm just taking a quick look at these. 5B. Okay. So question 2 and question 5B actually kind of relate to each other. They're both our theoretical understanding of what's happening with an atom and emission spectroscopy. So I'll read these out a little bit more carefully in just a moment. Mastery question set 3, problem 2. It's a kind of long question, but it says, which of these transitions corresponds to absorption, which emission, and which to emission of radiation? on your own piece of paper at home, draw out an energy diagram, and like the one depicted in the problem, and illustrate the transitions. And then it's got 1, 2, 3, 4, 5, and it does the 5 different things. So this is trying to get us to think about some interesting ideas in terms of atomic behavior versus light behavior, right? So an atom, when we start thinking about some of the stuff we learned last week, we've got a nucleus, we've got an electron. Electron is orbiting. I don't like the word orbiting, but electron is around the nucleus someplace. There's an attraction, there's an energetic interaction between the nucleus and the electron. And when we start solving for that energetic interaction, we find that we've got, instead of having any possible value, we've got answer sets. And so we've got answer set 1, we've got answer set 2, we've got answer set 3, we've got answer set 4, answer set 5, answer set 6, and we can keep going. It actually goes all the way up to infinity. It gets a little bit silly as you get higher because the lines get so close together that it starts to just become a big smear. And it's just asking us to consider what we get for different transitions. So if we go from 2 to 5, if we go from 2 to 5, there's a direction to this, right? This is an electron going up in energy. So that electron is gaining energy, which means photons of light must be absorbed. We've then got 3 to 1, and we can draw 3 to 1. That is going to be an arrow down. The atom is losing energy, so that means a photon must be coming out. Like the way that this electron is going to be gaining and losing energy, and it's really the electron around the nucleus in the atom, is either going to be absorbing a photon or emitting a photon. We've got 5 to 3. That is also going to be an emission. And then we've got 3 to 4, which is going to be absorption. And you'll notice each of these lines has a different length to it. And since this is on an energy scale, those different lengths of lines are going to correspond to a change. What color do I want to use? Let's do this. Each of those lengths of lines is going to correspond to a change in energy of the atom. And that's going to get us to, it's not going to be exactly equal to, but that's going to be energy of a photon. The reason it's not exact is because the photon doesn't care whether you're gaining or losing, right? If I, just for fun, look at the 1 to 2 versus the 2 to 1, absorption or emission. There's a pointing direction to those lines. Absorption is when the atom, the electron in the atom, goes up in levels, going to higher and higher energy, and the emission is when it goes down. You notice the delta E for this is either going to be positive or negative, but it's going to have the same magnitude. Whether it's positive or negative, that delta is going to be the same size, and it's just a sign flip. When we look at the energy of the photon, the photon always has to be positive energy. Whether it's a photon being absorbed or emitted, the photon is going to be positive energy. So that's what problem 2 is trying to get us to think about. And it says, for question B and C, write your response in the Roman numerals. So for one transition listed above, which correspond to emission, and then part C is for which ones correspond to absorption. So I kind of color-coded it. My blue lines are absorption, my black lines are emission. So that was part 2, and then we can go ahead and look at 5B. This is mastery questions. So question 5, 5A and 5B, is also looking at this idea of energy transitions. 5A has us calculate the energy in joules of the photon associated with a particular transition. In this case, it also involves different nuclei, so you're going to have some Z value. Z is atomic number, which you're not expected to memorize. You get it off the periodic table. So you get different ones randomly generated. Mine happens to be helium, so my Z number is going to be 2. And so I'll plug that in and do my calculations there. Most people seemed interested in 5B. Let me read that real quick. The emission line of one electron atoms and ions can all be fit to the equation describing the spectrum for hydrogen, which is blah. As the Z value increases, does the wavelength of the photon associated with the transition increase or decrease? Explain. So this is saying, how does increasing nuclear charge change the energy, the wavelength of the photon? So I like to think about it in terms of the atom energy. If you've got more charge in the nucleus, do you have more attraction or less attraction? Just yell it in your room while you're muted, it's fine. Right? If you've got more charge, that should be more attraction. Just to make sure we're all on the same page with that, if we're looking at the Coulomb force, and I think I actually wrote the Coulomb energy, you got Q1 times Q2 over 4 pi epsilon naught 1 over r squared. So that's charge 1 times charge 2. More charge means more energy. We can also look at it just in terms of the equation, the Rydberg equation for delta E of atom. There it is. The Rydberg equation for delta E of atom is equal to negative z squared RH 1 over n final squared minus 1 over n initial squared. Right, so if we just look at this, if z goes up, delta E is going to be a bigger magnitude. Right, delta E is going to be a bigger and bigger, it's going to be a bigger and bigger negative number, but it's going to be a bigger and bigger number. And since delta E of atom is related to the energy of the photon, so as the absolute value of the energy of the atom goes up, the energy of the photon goes up, but we have to remember photon to wavelength is an inverse relationship, so the wavelength should go down, right? Increase in energy, decrease in wavelength. I really like this problem, not just because it makes us kind of think about it conceptually. Like, I love mathematics. I love crunching numbers. I love doing calculations, making plots of all of this stuff. But for me, it's really important to make sure we're also getting the conceptual connections as well. So I like getting that kind of connection. So that was, hopefully that was, did that cover 5B for you?
Yeah, I think that helped out. So basically, just to like summarize, what I'm understanding is basically the wavelength, E would go up because the magnitude would increase.
Yes.
Due to the Z increasing as well. But then because it's an inverse, it's 1 over the variable, it actually acts as an inverse. And so wavelength would essentially be going down.
Yeah. And for me, I will admit, I am not the best at thinking of inverse relationships. So I just try to think of everything in terms of energy first, right? I know the energy of the atom is going up, so I know the energy of the photon is going to be going up. If it's the same n final n initial, which it specifically says it is.
Right. Okay, yeah, that makes total sense.
Cool. Okay.
Cool. Thank you very much.
So that was master question 5B. So Caitlin, for number 5, were you talking about emissions question 5?
Yeah, I actually figured you it out this time.
Oh, cool, okay. I've already come to the end of the questions I have listed. I'm going to stop recording for a moment so we don't sit here with awkward silence.
I have a question.
let's go ahead and take a look at emissions question problem 3. It reads as such: an excited hydrogen atom relaxes to the ground state while emitting a 121.5 nanometer photon. What is the initial principal quantum number Ni of the electron in the excited state? This is actually not much more difficult than the other problems we've been looking at. However, the mathematics get a little bit ugly. Well, a little bit delicate, let's say. Because if we do it in the wrong order, if we miss a sign flip or something like that, we can get something that really doesn't make sense. So we're going to be looking at this. Let's write down the explicit information, 121.5 nanometers, ground state, emission. Right? These things are all the clues that kind of tell us what kind of problem we're going to be looking at. The fact that we've got a wavelength that's emitted and we're talking about ground state, that should give us the clues that we're looking at a Rydberg type equation, Rydberg type problem. So since it's emission, we've got two options. We can do change in energy of the atom is equal to negative z squared RH times 1 over n final squared minus 1 over n initial squared, where we know, because it's ground state, we can infer the fact that that means n final equals 1. Since it's emission, we know that n initial is greater than 1, but we don't know how much greater than 1 it is. Now, the thing we have to be careful about here, we can also get this is inferred that the energy of the photon is going to be equal to hc over lambda, right? These things in parentheses are what we're supposed to be able to figure out from what the problem is saying. The place we have to be careful is that connection. If you remember the few times I've written this down, I've said absolute value of the atom energy is equal to the energy of the photon. If we look at these energy levels on our energy plot, n equals 1, I'll just draw a couple. We don't know which one it's coming from, but we know the atom is going to be losing energy. The energy of the atom has to be less than 0. It has to be losing energy because it's dropping in energy. So the energy of the atom, the change in the energy of the atom is going to be negative. We can also see that because n final is going to be a smaller number, n initial is going to be a bigger number. There's going to be a negative sign in there someplace. It's negative, right? But the energy of the photon has to be greater than 0. So we're going to have a sign flip when we're looking at this if we use this energy of the atom equation. So we have to be careful about that. One way that we can force the sign flip is we can also use the other version of the Rydberg equation. Right? So this version of the Rydberg equation, which they mentioned in the textbook, I've mentioned in office hours a couple times. It's also mentioned in Dr. Neff's emission spectrum video. This one only works for emission, and N1 has to be greater than N1 has to be smaller than N2. This statement right here guarantees that we get a positive value here, right? If we did this, and you can see how these relate to each other. This is like the absolute value was taken, so that negative disappears. So this is kind of taking that absolute value into account already. So if we've got emission, this one's a little bit nicer to use because it makes it so we don't have that hiccup of an extra negative sign. I like this equation better because it has me think about the physics and the chemistry that's actually going on, but I have to be careful about the sign flip. And I have to recognize that this energy, I have to make sure I've got that as a negative energy because it's losing energy. But let's go ahead and do it with the easier equation and see what we've got here. I'm going to start plugging in the values I know. I've got 1 over 121.5 nanometers. Got to do my conversion. So I'll multiply by 1 meter. Has 1 times 10 to the 9 nanometers. That's going to be equal to, I didn't give myself enough space. That's okay. This is a hydrogen atom, so z squared is equal to 1. The Rydberg constant for this version of the Rydberg equation is that 1. I'm going to check the equations sheet. I did have it. Okay, 1.097 times 10 to the positive 7 meters. And then I'm going to have times 1 over n1. n1 has to be the smaller value for this case. So I'm going to use the ground state value of n, which happens to be 1, minus n2 squared. And now we have to solve for what n2 actually is. So at this point, we've done our kind of sign flipping thinking through doing our energy thinking. And now we just have to do algebra. I say that like algebra is trivial, but but this is kind of the least trivial algebra we do this quarter. It's really easy to make mistakes here. So important things: using the correct Rydberg constant, converting to meters. So that and this is 1 over meters. Converting from nanometers to meters, so our units match up. And then making sure you've got the order of the variables correct inside here, because if you get that wrong, that'll cause a sign flip as well. Some calculator work. You might have different values than me, but let's go ahead and do some calculator work and see what we get. Inverse. Oh, I forgot to hit the inverse button. There we go. Divide by 1.097 times 10 to the 7 equal to 0.750 is equal to 1 over 1 squared minus 1 over 2. Sorry. I'm going to call it x squared because that's what we're solving for. You know, we've all taken enough math classes that we're just programmed in our brains to solve for x. Is that good so far, Gabby?
Yeah, it's good.
Cool. At this point, I can, because I've done this type of problem enough times, I already see the train coming. I'm going to go ahead, I'm going to subtract 1, I'm going to do 0.75, I'm going to do a little flip-flop. I'm going to have negative 0.25 equals negative 1 over x squared. I'm going to get rid of the negative signs, right? 0.75 minus 1. Get rid of the negative signs. 0.25 equals x. I'm going to rewrite 0.25 as the thing that we all know as 1/4. And now we can almost see it already, right? We're going to get to 4 equals x squared or 2 equals x. Making sure you don't sign flip when you do the subtraction is a really big part. That's where using this other version of the equation can sometimes create a headache if you miss a sign flip. If you miss a sign flip, instead of getting 0.75, instead of getting 0.25, you'd get 1.75. You get something totally different. So you got to watch out for that. Which is why I always start with concept thinking.
Thank you.
You bet.